Next test we're going to look at is a direct comparison test. Suppose I have this series from 1 to infinity, from 0 to infinity of 1 over 2n. This is geometric. However, if I throw this in the numerator, it's not geometric, so I cannot find what this one is. And if I sum from 1 to infinity of 1 over n cubed, this is p series. But if I add this plus 1 in the denominator, it's no longer p series. Now, the third example is if I have a sub n is n over n squared plus 1, I can integrate this. But if I throw in another square, I can't integrate this. So I need a new tool, and that tool is a direct comparison test. Suppose I have 0 is less than a sub n, and a sub n is always less than or equal to b sub n for all n. So a sub n is smaller, and b sub n is the larger. Then if the sum of b sub n converges, then clearly the sum of a sub n converges. While if the sum of a sub n diverges, okay, and it's always less than the sum of b sub n, then the sum of b sub n must also diverge. Let's look at this. Suppose I have the sum as n goes from 1 to infinity of 2 plus 3 to the n. Well, this isn't a geometric series, but I do know that the sum as n goes from 1 to infinity of 1 over 3 to the n is geometric, and it does converge. All right. Now, let me look at a sub n is equal to 1 over 2 plus 3 to the n. And I'm going to show you that this is less than 1 over 3 to the n. All right. Now, it's kind of obvious by looking at it, but I'm going to cross multiply. I'm simply showing you that it's true. So this is a true statement. Therefore, I'm going to write the word true, by the direct comparison test, need space, the sum as n goes from 1 to infinity of 1 over 2 plus 3 to the n converges. Note, I can't tell you what it converges to. I can just say it converges. Now let's look at this one right here. 1 over 2 plus the square root of n. Now, you want to compare this to the sum as n goes from 1 to infinity of 1 over the square root of n. And we know this diverges by p series. So let's look at a term-by-term comparison. 1 over 2 plus the square root of n. Is this always less than or equal to 1 over the square root of n? So it's the square root of n. And lo and behold, the divergent series is greater than the series we're looking at. No, what I needed this to go the other way. I needed to show that this was greater than 1 over the square root of n. So this doesn't fit. So as much as I want it to, this one doesn't fit. So I need to try another series. Well, the next series that I know, and I'm suspecting that this always diverges, let me look at the sum as n goes from 1 to infinity of 1 over n. Let me do a term-by-term comparison of this one. If a sub n is 1 over n, is that less than or equal to 1 over 2 plus the square root of n? And for this one, we're going to have to restrict it. And let's see where we have to restrict it, because we really care about the sum. So let me see if this is true. 2 plus the square root of n is less than or equal to n. And I see that for n greater than or equal to 4, this is always going to be true. So I can say for n greater than or equal to 4, this diverges. Excuse me, let me go back up. I can say that for n greater than 4, this is always true. Remember, I don't care about the first 3 terms. So by direct comparison, all right, the sum as n goes from 1 to infinity of 1 over 2 plus the square root of n diverges. Now I do want you to remember, A has to be positive and less than or equal to B. If the larger term series converges, the smaller also converges. If the smaller diverges, the larger has to diverge.